Here are the solutions for the Ready, Set, Go Unit 1 Lesson 5 problems. Inverse universe. So, the Ready problems say, use property of exponents to rewrite the expression. Write your answer in exponential form with positive exponents. So it wants it in exponential form. So let's go over a few things to remember before we start. Right? When I have something in radical form, like this, the nth root right there, let's make it x to the m. I can rewrite that as just x to the m. That doesn't change, but now that nth root is shown as divided by n as an exponent. So there's some other rules we'll revisit as we get closer, but that's this first one we need. So let's start by rewriting this expression as x to the 2 over 7 times x to the 3 over 7. Okay, so this brings us to our next rule, right? If I have x to the n times x to the m, remember when I multiply terms with the same base, I add their exponents. So I can add n and m. So in this case, they have a common denominator of 7. So I can go ahead and add 2/7 plus 3/7 to get x to the 5 over 7. So that is an exponential form with positive exponents. So we have completed our task. Okay, so this next one, again, let's start by rewriting this as exponents. So there's a little imaginary 1 there. So 1/3 times x to the, again, there's no number, so 1/4 times x to the 1/6. And you don't have to add those little ones on there, but I do find it helpful sometimes. So we do not have common denominator here, so that's the first thing we want to find, a common denominator. So 3, 4, and 6, our lowest possible common denominator here is 12, so we'll use 12. If you're struggling to find one, you can always multiply the numbers entirely together. 3 times 4 is 12, times 6 is 72, but that's going to be much bigger than we actually need. So to make 1/3, well, to get that to be a 12, we need to multiply 3 by 4. So to not actually change the value of the expression, I have to do 4 over 4, because that's equivalent to multiplying by 1. So I get 4 over 12. So that first term can be changed to x to the 4 over 12. So our second term here, 1/4. Again, to make that a common denominator of 12, I need to multiply 4 by 3. So I do 3 over 3. So 3 over 12. So x to the 3 over 12. And then lastly, 1/6. Well, to get 6 to become a 12, I need to multiply 6 by 2. So I have to multiply by 2 over 2. So 2 over 12. So we now have a common denominator, which is excellent. We can add these numbers together. We can add 4 plus 3 plus 2. So 4 over 12 plus 3 over 12 plus 2 over 12. So that brings us to, let me not zoom out too far here so you can continue to see the rest of the problem. Well, 4 plus 3 is 7, plus 2 is 9 over 12. And we can always reduce, or we should always look to reduce. They have a common factor of 3, which means I can reduce both by 3. So this becomes x to the 3/4. So exponential form with positive exponents. Perfect. All right, let's move on to our next one. So our next one, we see that one of the terms is b. So we're not going to be able to get this down to one term, or one value only. I shouldn't say term. This is one term. But instead, we can definitely combine these a's. So let's focus on that. Let's do a to the 1/6 times a to the 2/3. And we'll rewrite the b in exponential form, b to the 3/5. But since it's not the same base, I can't add those exponents together. So 1/6 and 2/3, well, again, we need a common denominator. This time, let's make that 6. So the 1/6 is already set, so 2/3, well, to make that something over 6, I need to multiply 3 by 2. So I do 2 over 2. So 4 times 2, this becomes 4/6. So a to the 1/6 plus 4/6. I'm going to skip the middle step of rewriting that, since we can see that's where that's coming from, times b to the 3/5. So that becomes a to the 5/6, and I can't reduce that anymore, so I'm going to leave it as 5/6 times b to the 3/5. Now, if we really wanted this to be one radical symbol, if we were to put it back, we would need a common denominator between these two, which I'll kind of do off to the side. You don't need to do this, so I'll do it kind of on the faster side. They both can be written as something over 30, right? 25 over 30 is the same as 5/6. And b, well, if I multiply 3 and 5 by 6, I get 18 over 30. Now, the reason why this would be helpful is this can then become a to the 25th, b to the 18th, and I can actually raise that to the 1 over 30. So I could write them in exponential form this way. That way, if I wanted to turn that back into a radical, they'd be under the same radical symbol. Not really needed, but wanted to sort of add that extra tidbit. All right, let's look at our next one. So here we have numerical values instead of variables. So we can still start with sort of our initial set of directions, write this in exponential form. So 32 to the 1/5 times 9 to the 1/2 times 27 to the 1/3. So we really finished the directions here, but it is good to reduce our numbers where possible and combine numbers if possible. So 32, I can't write that as a base 3, but I certainly could with 9 and 27. But before I go and change the base, let's see if these simplify nicely. So 32, we might not know the 5th root of 32, but hopefully we can at least start to sort of break it down. So this becomes 2 to the 8. Let's see, and 8 is 2 times 4. We get 2 times 2 here. So I have 1, 2, 3, 4, 5 2's. So in fact, the 5th root of 132, of 32, or 32 to the 1/5 is actually just 2. 9 to the 1/2, well, that becomes 3. The square root of 9 is 3. And 27, well, that's 3 times 3 times 3. So I said square root. I meant to say the 3rd root. I am misspeaking left and right here. I'm sorry. So we end up actually with 2 times 3 is 6, times 3 is 18. So the reduced form of this is just 18, or 18 to the 1st power if you want to write it with positive exponent. So whichever way you want to sort of go about that one, that's okay. This next one, I see a bunch of 2's. So we actually could, again, combine these if we make them all base 2, but we'll do that second. First, let's do 8 to the 1/4 times 16 to the 1/3 times 2 to the 1/6. Okay. So 8, if I want to write that as 2 to some power, 8 can be written as 2 cubed to the 1/4. And I don't need those parentheses. I'm just want to do this step by step. Well, 8 times 2 is 16, so 16 is 2 to the 4th power times 1/2. And then 2 to the 1/6, we can't really simplify that more than it already is. So I don't want to zoom out too much. So this becomes 2 to the 3/4 times, well, 4 times 1/2 is just 2 squared times 2 to the 1/6. So I could combine these with a common denominator. Let's do that. I could also separate that 2 squared. I could make that 4. 4 and 6 are common denominator there. would be, our lowest common denominator is 12. There's lots of common denominators. Our lowest one is 12. So 3/4, I need to multiply by 3 over 3 to get 9 over 12. And 1/6, I need to multiply by 2 over 2 to get 2 over 12. And let's do the 2, I guess, why not? I kind of skipped it there. But 2 is the same thing as 2 over 1. So if I want that to be over 12, I have to multiply by 12 over 12, or 24 over 12. So this problem becomes 2 to the 9 over 12 plus 24 over 12 plus 2 over 12. So I'm running out of space here. Let me just make this a little bit smaller, give us some more room to work. Okay. Well, since all our denominators are 12, I can add 9 plus 24 plus 2. Right? So that gives me 12 as my denominator. Well, 9 plus 2, let's do that first. We get 11. 11 plus 24 gives us 35. Or if we want to think of it, if we do want to separate that this one out here, we can take 24 away from that. So 2 squared times, well, 11 over 12. 4 times 2 to the 11 over 12. But I think it looks nicer just to have it as one answer in exponential form. So, we'll just keep it as 35 over 12. But just showing some things you can do to manipulate. All right, let's get back on track. So here we have the same rule we've been kind of working with, but I'll write it out explicitly. Right? If I do have something, one exponent raised to the power of another exponent, that's actually when I multiply them. And I've used that rule in some of the problems above without really talking about it. So this becomes 5 to the 6th. It says leave it in exponential form, so we won't multiply that number out. Negative exponents. So remember, with negative exponents, if I have something like x to the negative 1, it creates its own reciprocal. It goes to the opposite side of the fraction. So x to the negative 1 is 1 over x. So when I have this 7 squared all in parentheses, I could distribute my negative. I could make it negative 2, which would then become 1 over 7 squared. Or I could think of this whole thing as one unit, and the 1 just creates, turns it into being the bottom of the fraction. We end up with the same term either way. Again, 49 we can probably do in our head, but it says leave in exponential form, so I'll leave it as 1 over 7 squared as my final answer. Okay, here we have a double negative. So remember, we multiply these two, which means negative times negative becomes a positive, 3 to the 20th. I could have tried to flip and do all these things with the reciprocal rule for exponents, but I think in this case it's easier to let those negative signs cancel each other out. So here, again, there's actually a bunch of ways we can do this. These are all exponents. I'm going to move this 5 to the negative 4 down the bottom first. I don't have to do that first, but I'm going to do that first. So we're going to make that 5 to the positive 4. 5 squared is already a positive exponent, so that does not move. That doesn't go anywhere. Now I'm going to combine my 4 and 2 with addition. Right? 5 to the 4th times 5 squared becomes 5 to the 6th. And this whole thing is still being cubed. So when I cube something, I cube the top and bottom. So I get 1 cubed over, 5 to the 6th cubed becomes 5 to the 18th. But 1 cubed is just 1. So 1 over 5 to the 18. If you had done this in a different order, maybe you did 5 to the negative 12 over 5 to the 6th, we would have still gotten the same answer. So we'd have to bring that 12 down to make it positive. And then 12 plus 6 is 18. So different order, same final result. Okay. let's move on to the set problems. So for our set problems, it says write the inverse of the given function with the same representation as the given function. So it gave us a table. It wants us to write our answer as a table. So inverse, right? Remember our input and output. Switch. So all my inputs there that are shown by x, -8, -4, 0, 4, 8, those are going to become my outputs and vice versa. So this becomes 0, -8, 3, -4, 6, 0, 9, 4, and 12, 8. And that's it. That's problem 10. Okay, problem 11. So it gives us, this time it gave us a graph. So I want to show a graph. So there's a few ways you can actually think of the graph, especially if you're a visual learner. Inverses, we're switching our inputs and outputs, right? So I'm going to take my y values and I'm going to make them equal x and vice versa. So inverses are symmetric about or over, however you want to phrase it, this y equals x line. So I'm going to dot that in just so we can visually really see it. Not my best line here, but pretty decent. So it's going to be symmetric over that line. So that's one way to think of it. Another way to do it is to actually just pick out some points. If you're not such a visual learner and you have points, I'll do the original function first. You can always pick some out. For instance, this point here, we have 0 for x, and we're down at -3 for y. So if we have 0, -3 as our point of our original function, that means the inverse equation is going to have the point -3, 0. Right, this is another nice clean one. So we have 2, 0 here. That means we're going to have 0, 2. Now the problem with using this method alone is it doesn't sort of paint a picture of what's happening in between or, at other points. So let's just put one more point here. This looks like, what is that, 4, 11? So we have 11, 4. So if you aren't a visual learner and you want to pick some points out, that's great. But it's good to always sort of look for asymptotes in other key characters as well. Here we have a horizontal asymptote. At y equals, let's see, it looks like it's hitting it right at -4. So horizontal asymptote in the original function means its inverse is going to have a vertical asymptote at x equals -4. Let's move that up. That's not really... I try to insert some lines here to make it clearer. But my pen wants to be a little funky with me. There we go. That looks much better. All right. So that means we're going to have a vertical asymptote. At x equals -4. Right, our input and output are switched, so that's x and y in switching. So here's 1, 2, 3. Here's our -4. So I like to dot it there with a line. I don't actually have to show that, but it makes it a little bit easier to see the asymptote when we're hand drawing it. And I'll plot some of these other points, right? I'll plot my -3, 1, 2, 3, 0. I'll plot my 0, 2. And I'll plot my 11, 4, if it fits. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3, 4. So these points are giving me a pretty good shape. A good thing to always do is sort of think about what's happening to x and y. Like here, as x grows, so as x is going to the right, or is going towards infinity, y is also going towards infinity. So that should actually stay the same. since they're both infinities if I switch out x and y. But here, as x goes towards negative infinity, y is going towards negative 4. So that's what we see here this time as y goes towards negative infinity. I'll write this out actually. As x goes towards negative infinity, or the left, y is approaching negative 4. So for this one, our vertical asymptote, that y and x is switched this time as y is going towards negative infinity, x is going towards negative 4. So y going toward negative infinity, that just means as it's going down. So I know that we should be going downward as we're approaching that asymptote, since we're going in the negative direction on the original one. So it tells me which direction I'm going in. And now we're just going to connect those points. And there we have it. Again, you could have gotten this by visually seeing, like, for instance, this segment here. Well, that's what, if I draw my, part of it anyways, there we go. That's what I'm seeing right there. I'm seeing it flipped over that y equals x line. Same thing if I extend that line out. Instead of up here, I'm seeing it down on that. Instead of sort of top side of that y equals x line, I'm seeing it on the bottom side of that y equals x line. So visual learners, it's a little bit quicker just to sort of look at the graph and flip it over that line. And we'll do that for the next problem. Okay, anyways, problem 12. So here they give us an equation this time. So when we want the inverse function, sometimes I like to just write it as y to start to make my algebraic work a little simpler. We're really solving for this input value. So solve for x. Some people like to say switch your x and y and solve for y, but I'm just going to say solve for x here. So I want to undo everything, right? I want to undo my plus 4 with a minus 4. So that becomes y minus 4 equals negative 2x. And then I want to divide every term by negative 2. So divide every term by negative 2. Now I could leave this as a big fraction, but so that it looks linear still. Y over negative 2, I'm going to write that as negative 1/2 y, and negative 4 over negative 2 is positive 2. So it wants it in this form, where it wants x to still be our input. So now that's going to be our new x, even though it was a y. I'm going to just write equals negative 1/2 x plus 2. Because x and y are pretty arbitrary. It's whatever value we give them. So here we're saying x is still the input, even though it's now what was considered y. So that is now the input of the inverse. But we're going to rename it as x again. Okay, problem 13. So problem 13, we have a graph again. So this one I'm going to try to do without showing a table. You can absolutely still use that table method, but instead I'm just going to sort of highlight key parts and see if we can do it there. So here, if I look at the top right, so as x is approaching, I'm going to pause for 1 second. Okay, I'm picking back. Now I know I paused the video, so there's no breathe. Sorry if there was some music in the background. I was waiting for the people near me to walk by and finish, so I apologize for that. Now there should be no background noise. But basically, as we go to the right, our graph is going up. Right, so right and up and left and down. We see that this 0, 0 point, it hits at the origin. So that actually doesn't change. It's still going to hit at the origin. 0, 0. And I'll label that. So now, I see this point sort of 1, 1. So I'll count by 2s here. I'll make this 1, 1. And I also see that it goes to this negative 1, negative 1. So those points, notice they don't change because x and y are the same. So flipping my input and output actually doesn't impact those 3 points. However, notice the curve. We're curving underneath here. Right? If I draw that y equals x line in, I'm sort of underneath that curving. So it's inverse. I want to be above it curving. And here, I'm above the line. So here I want to be below the line. So those are how those 3 points connect. Now, if I look at this part here, I'm going up pretty steeply as I go to the right. So I'm going to go pretty steep horizontally this way, right? I'm going to kind of mimic that shade, that shape this way. I'm going to make that look a little bit more. There we go. Okay, I'm not labeling any other points. I could see that this is cubic, and I could do 2, 8 if I wanted to, right? Let's see. Well, I counted by 2, so I can't even fit 2, 8 on here. But in this one down here, make that a little bit better. Yeah, we're going pretty steep horizontally. So before we were pretty steep vertically, now we're pretty steep horizontally. And there we go. That is our inverse. Okay, question 14. We have another equation. So off to the side, I'm going to write 13 minus x. And I'm just going to replace my f of x with y. So again, we want to solve for x. So I will subtract 13 first. Right, I'm going to move that over to this side. So it's positive on the right side. I'm going to make it negative on the left side. And then I want to divide or multiply everything by -1 to get rid of that negative sign on the x. So negative x plus 13 equals, negative y plus 13 equals positive x. So again, this is my new input, which we're going to rename x, since it wants the input to be named x. And in this part right here is what becomes f inverse of x. So f inverse of x equals negative x plus 13. Notice it's actually the exact same equation. So that happens sometimes. If we want to really consider y, well, we can look at the graph of it. So this one is saying that our y-intercept is positive 13. This is the original graph. And we're over 1, down 1. Our slope is -1, which means it's going to actually bring us to 13, 0 here. So all those points, so we see that x and y are the same. That's a quick snapshot of seeing if we switch x and y, it actually wouldn't change the graph. And we can fill in the points along the way, but that's a nice little snapshot of it. Okay, so let's go down to problem 15. So 15, it gives us a table and a graph. So very similar to how we did question, which one was it? Question 11. So very similar to how we did question 11. Only for 11, we created our own graph. So let's start with the table. We created our own table for that other question. So 0, 0, that point's not going to change. So let's go ahead and plop that on there. This one, 1, 1, also doesn't change. But now we're going to have 4, 2, 9, 3, and 16, 4. So we want to be sort of careful here. Because notice the axes don't count the same value. So I'm going up by tens on my y-axis, which means I want to make sure my x-axis sort of has that same pattern. Now, we have a lot more dots here, so I might not have to go by tens, but maybe 2. So let's make this 4. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I'm already at 20. That's good. 22, 24, 26, 28, and there's my 30. So I got the same values in. And here, our x-axis is counting by ones. So that one really, we don't need a lot of numbers there. I'm going to actually count by 0.5. So I'm going to make this 1, 2, 3, 4, 5, 6, and that's how far they went. So we really don't need to go much further than that. We're going to show the same representation. If you counted by something slightly different, that's okay, as long as your graph sort of still resembles the inverse. So we have all these points, so let's go ahead and plot them. So 1, 1, well, we're counting by 2, so this is really right there. 4, 2 becomes right here. And I'll do some labeling, sure. 9, 3, so 9, 3. And then 16, 4. So I can already kind of see the pattern of connecting, but it's always good to sort of visualize this, right? Here's our, well, I can't really draw y equals x in cleanly because the scale is not the same. So be really careful that when you're trying to draw that line of y equals x to show the symmetry, it's much harder if your scale isn't the same on x and y, which is why the table is really helpful in this particular problem. So I see that it has that sort of downward curve, right? We're going to call that concave up, increasing eventually. So it has that concavity where it's increasing at an increasing rate. It's getting faster and faster. It's getting more steep as we go on. So this one, we're gonna flip that. We're gonna have it bending downward and sort of getting less steep as we go along. So it starts steeper and gets less steep. Okay. And there we have it. There's our inverse. So now our go problems. It says calculate f of g of x and g of f of x for each pair of functions. So to give us more space, I kind of copied these over on the side. So number 16, I'm going to go right over here instead. So f of g of x. So let's write our function for f of x. But I'm going to replace my x values with g. So g of x is negative 4x minus 11. So we just have to make sure we distribute. So 3 times negative 4 is negative 12x. And 3 times negative 11 is negative 33. We have that plus 7 at the end. So this becomes negative 12x minus, well, negative 33 plus 7 becomes minus 26. Okay, there we go. So that is f of g of x. For g of f of x, we start with the function g of x. So that's negative 4. Everywhere I see an x, I'm going to leave sort of an open space because I want to use f of x as my new input. So I'm going to put 3x plus 7 where our x was. And just like the last problem, we're going to distribute that negative 4 to get negative 12x minus 28. And then that negative 11 is just kind of tacked on at the end. So if I combine my like terms here, right, I get negative 39. So there's g of f of x. Okay. So let's just move those onto our page here. And there we go. Really small in there, but that's okay. Actually, oh, there we go. Okay. All right, let's go to 17. So 17. There we go. So f of x. So f of g of x. Well, I'm going to start with negative 4. Leave a parentheses where my x is, plus 60. And for my g of x equation is negative 1/4 x plus 15. So now I distribute. Negative times negative gives us a positive. 4 times 1/4 is 1. So positive 1x, or just x. Negative 4 times positive 15 gives us negative 60. And then I have this other 60 at the end. So negative 60 plus 60, those reduce to 0. So I'm just left with f of g of x equals x. Now this is actually a sign that I don't need to calculate all of g of f of x. If one of them came out to just x, they're both going to come out to just x. They're going to undo each other completely. But just to show that transformation, let's actually calculate it. So I filled in my g of x, left my hole for where I'm going to put in f of x. So I'm going to fill in negative 4x plus 60 as my input. So that's replacing x. And now let's distribute. So negative 1/4 times negative 4 becomes 1x, or just x. And negative 1/4 times 60, or 60 divided by negative 4, we get negative 15. And I have that positive 15 tacked on at the end. So those reduce to 0, and I'm left with, once again, just x. So there we go. There's number 17. Let's just put that up and put it with 17 there. Okay. All right, now 18. Let's zoom into 18. So 18, our f of x equation is 10x minus 5. So f of x, 10x minus 5. But remember, instead of writing x, I'm going to leave that space so I can fill in the equation for g of x. G of x is 2/5 x plus 3. Okay, so let's distribute. So 10 times 2/5. I like to do 10 divided by 5 first. So that gives me that 2. And then 2 times 2 is 4x, right? So 10 divided by 5 first is 2. 2 times 2 is 4. You could also do 10 times 2 is 20. 20 divided by 4. 20 divided by 5 is 4. All right, and then 3 times 10 gives us 30. So we end up with f of g of x equals 4x plus 25. So we see that they are not inverses. They didn't undo each other entirely. That is okay. So g of x, I'm going to leave a space to do a new input. I'm going to do 2/5 times something, and that something is going to be our equation for f of x. So f of x is 10x minus 5, so that's what we input into g of x. So let's distribute our 2/5. Well, we already did 2/5 times 10, so we don't have to redo that, but remember 2 times 10 is 20. 20 divided by 5 is 4, or 10 divided by 5 is 2. 2 times 2 is 4. Here, 5 and 5, those cancel each other out. Those reduce to 1, so I'm just left with 2. You could also do 2 times negative 5 is negative 10. Divided by 5 is 2, or negative 2. So we end up with 4x plus 1. Okay, that's g of f of x. So that's problem 18. Just kind of put that in there. And then I'm just going to make sure we are super clear in dividing those up, so when we look back at our work, we can really see which problem is which. Okay. Let's go down to problem 19 now. So 19, I give myself some space for that one, so we'll do it off to the side here. So 19, we have negative 2x plus 4 as our function for f. Oh, sorry, negative 2/3. I'm going to leave a space where the x goes, plus 4. I'm going to fill in my g of x. So g of x is negative 3/2 x plus 6. So now let's distribute that negative 2/3. Well, 2/3 times 3/2, those are going to reduce down to 1. So negative times negative is also positive. So that just becomes x. 6 divided by 3 is 2. 2 times negative 2 is negative 4. Or again, negative 2 times 6 is negative 12. Divided by 3 is negative 4. And then I have that plus 4 at the end. So this just becomes x. So f of g of x is x. So now let's do g of f of x. So our function from g starts negative 3/2 x. So I'm going to leave a space, and I'm going to add my plus 6 at the end. Now let's plug in our new input, f of x. F of x. So negative 2/3 x plus 4. And once again, we're going to distribute. So we already determined that negative 3/2 times negative 2/3 is just positive x. Negative 3/2 times positive 4. Well, 4 divided by 2 is 2. So 2 times negative 3 is negative 6. And then we still have this plus 6 at the end. So those reduce to x. So once again, we got a function that reduced to just x. So let's move that over. That way if we want to go back and scan up and look at these, we have them right where they're supposed to be. Okay. All right. So question 20 says, look back at your calculations for f of g of x and g of f of x. Two of the pairs are inverses of each other's. Which pairs do you think they are? Why? Well, the pairs that are the same are pairs for 19, and are pairs for, sorry, I shouldn't say the same. Which pairs the pairs that are inverses are pairs that came out to just x. So 17, I'm going to redo that. There we go. And 19. And let's talk about the y. So, our pairs from question 17. So this is number 19 and 17. So, f of x and g of x. So look back at your equation. Two of the pairs of the equation are inverse to the other. So since when we composed of the pairs of equations from 17 and 19 from question 17 and 19, the result was 0. The result was not 0. What am I saying? The result was 1, positive 1, x or just x. I'll just write it as x. They are inverses. Right? They completely undid each other. Right? So when we think about what it means to be an inverse, we said x and y are switched. So it's symmetric about y equals x. Like if the only thing left over is that x in the end, that means that sort of our outputs, this is the output, is just x. So our output is just x. It undoes all the addition, all the subtraction, all the exponents, and any multiplication, division. It undoes everything. So what's left is whatever we inputted in the first place. That means the input of 1 was the output of the other. So when we switch that input and output, they don't change. All right, and we'll leave it at that. So hopefully that video was helpful, and